What have you been doing?
Well, we had two ideas last time. One about the sort of this wildly ramified extension,
Right.
and to see if the larger extension, whether we can deal with that.
Mm-hmm.
And the other thing, I wanted to follow up on Basarab's work and Tati's work as well. Right?
Very good.
And I actually took the time to read most of Basarab's paper.
Mm-hmm.
And I think I'm quite optimistic now about whether we can, or I'm optimistic that this claim about projective or inverse limits is probably actually true in general.
Okay. And that's already hidden somewhere in Basarab, or?
That is somehow hidden in Basarab. We had most of the ideas before, I think.
Okay. So what was missing?
What was missing? One condition on the inverse limit system, actually. I think.
Some kind of.
So I might try to, try to write down the theorem and we can see if it's right.
Yeah.
Let's say we have just rings.
Okay.
And I think we can have any inverse system, but we can assume for the moment that they're just countable.
Yeah, fine.
So I think the assumption, it's not enough to assume that all the rings are elementarily equivalent, component-wise.
Mm-hmm.
And I think one can cook up counter examples for that. Maybe not for inverse limits, but at least for direct limits. I guess if we just take z, and we take, for example, multiplication by 2 and multiplication by 3,
Right.
this will give different rings, right? So I take the direct limit of this system, I should get something like 1 over 2 infinity z.
Right.
And here we'll probably get something like 1 over 3 infinity z.
That means you want all those squares to commute.
I can't say that because there are no maps here.
So what can you say then instead?
What I want is every ring to be somehow interpretable in the pre-image, or in the previous, or in the ring that lies above. Or potentially I could say if they are all surjective, I want the kernel to be definable.
Yeah.
And the defining formula should be the same for both systems.
Right. Well, that makes very good sense.
So I think there needs to be some definability condition on the maps.
Yeah.
I think we can't just have arbitrary maps and they have no structure whatsoever. I think we have to assume that
that sounds very natural. Yeah.
Have some definability.
Mm-hmm. Mm-hmm.
So.
Okay, very good. So you haven't written it up properly yet?
I haven't written it up properly yet. But
that sounds like the right approach, yeah.
And sort of the idea that makes it work, I think, is so if we are, let's say, in a saturated setting, L(1) saturated setting.
Okay, so we are no longer countable. Oh no, they're just asking for countably many copies.
Well, I would say we have countably many components.
Okay.
Or rings that make up the system.
Okay.
But I guess the idea is that almost sort of we're trying to prove embedding theorems, and it would be enough if we could, let's say, for any finitely many formulas with constants, let's say from one system, if we could realize it in the other system. So
yes, that makes sense. Yeah.
For any finite set of formulas with parameters from here, then that would give us that sort of the elementary diagram of the above system is satisfied in the one below.
Right.
And if we have that for inverse systems in language of inverse systems, then we could take the limit, and taking the limit, we will actually get somehow, in some form, an actual embedding.
Yeah, elementary.
first, I think not elementary. Or for the start, it will not be elementary.
Oh, because these are also not elementary.
So at the moment, they're not elementary.
Yeah, they're just equivalences.
I think this is an important point, that we don't want this to be elementary when we prove our embedding lemmas. Because that would mean we already know how to transfer from inverse systems to
I see. Yeah.
to the limit,
Yeah.
which we don't know.
Yeah.
So we actually want like the in-between step of having embedding theorems,
Right.
and then sort of building up some chain and then some Tarski argument that will give us.
That sounds like a very good approach. Yes.
So something along the lines, like we start out. Let's say I call the inverse system R dot and S dot.
Okay.
And I guess I would first look at an elementary extension, like this.
Mm-hmm.
And then I would, and I also look at an elementary extension here, which is saturated enough. And then I can find an embedding like this.
Mm-hmm.
And then I look at an elementary extension.
Keep going like this. Yes.
I keep going like this. Then I embed it to here. And then I continue this ladder sort of type embedding.
Oh, you make it back and forth?
Yes, this is a back and forth argument.
Okay.
And then when I take the union, which is then the direct limit, when I take the union, I get some inverse system. I get two, I guess, then isomorphic inverse systems.
That's right, yeah.
Which are elementary embeddings of the original ones.
Okay.
So something like this.
Right, yeah.
Which then will become elementary equivalent. So this,
yeah, very good.
and so these embedding theorems, they will only work in a saturated setting. So the image will have to be somehow saturated.
Yeah.
For this to work. And the idea how to get these embeddings of the inverse system is the same as the existence of an inverse limit in the first place.
Right.
But one has to use the property on the maps. So usually we just need surjectivity of the map somehow.
Right.
And here instead we use the probably interpretability.
Yes.
So if we have constants, let's say from one member here, from one member here, and from one member here, then we can sort of push the constants all in one, or the formulas, we can push the formulas all to one ring.
Oh, right, yeah.
So we have finitely many formulas with constants from different rings.
Yes.
But with some interpretability, we can push them to one ring.
Right.
And if we can do that, then the fact that, let's say this is saturated, we get an embed.
Makes you realize.
We have an embedding component-wise.
The type, yeah.
And it makes me realize the type in this ring, which then gives us the real. Then we know that the initial conjunction will be realizable in this ring.
Right. Yeah. That's very nice. Yeah.
So this is just the general structure of the proof, and I guess.
But it looks like exactly the right thing to ask for, that the kernel be definable in each of these.
And I guess one can have probably a few more general conditions on that.
Like what?
Like interpretability. I guess we just want formulas that are true in here, or we want that the formula is true here, if and only, let's say it's somehow pullback is true in the one above.
Oh, I see, yeah. Yeah.
And that is probably even more generally true, probably even if the kernel is not definable. But in most applications, the kernel will be definable, I think.
Yeah. So yeah, let's start with that and then see how we can sort of loosen the conditions. But in our situation, we can always arrange it
Yes,
to be like
exactly.
that. So yeah. Well, brilliant. That's yeah. looking forward
To making that precise.
to see that being made precise. Yeah, that's brilliant. Excellent. Yeah. No, I think that's exactly how it should work. And that is all more or less already in Buzzer Up.
Yes, but he does it in a different setting. He has these mixed structures. Let me take a different color. So his predicates are somehow I guess. So he has these value group like multiplicative groups. This is one of them, and he also has these rings.
Right.
And he has even like a map from one to the other.
Yes.
Which is not defined everywhere on the ring, but never mind.
Okay.
So, and this is awfully close to, so this is Basara.
Mm-hmm.
And elementary setup is
very similar.
It's very similar. It's actually these reduced rings.
Yeah. Yeah.
And I believe one can translate one to the other if one is clever enough with some exact sequences here.
Yeah, I'm pretty sure this is doable. And possibly Kostas has done it already?
No, I think he does not use Basara at all.
Okay. Interesting.
So there's like a bit of work to be done here.
Okay, oh that's great. Yeah, very good. Okay. Shall we
move to a different
move to the other?
Yes.
Okay. So it's about extremality. I've thought a bit about extremality, and two things occur to me. So what we want to be extremal is we start off obviously with our core object QP abelian, and there's somewhere there is the algebraic closure of QP abelian, and what we want to be extremal is the smallest intermediate extension with divisible value group, because we know the value group has to be divisible, and that is just the fixed field of the ramification subgroup of the absolute Galois group, and this is a purely ramified Z hat dashed extension, where this is just the product of all primes different from P.
Yes.
So the hope is that this guy is extremal. And the next hope, well, this may or may not be true. We can try to prove that directly. But if this is extremal, of course, it would be nice to put that into our axioms here. However, that is an infinite extension, and being extremal is saying something about polynomials in two variables, that the maximal value is actually attained. But we can talk about a polynomial in two variables here that has only finitely many coefficients, so it lives in some finite extension there. That is definitely something we can talk about in the first order way downstairs. But then it's saying, to this polynomial, there exists somebody here such that, and this somebody here, if we have a bound for where that lives,
So the complexity, yeah.
the complexity, then we can formulate it in the first order way. So if there's a degree 15 extension here, and we know that where the coefficients live, and if we know that that maximum coming from extremality is obtained in at most a degree 15 factorial extension, then we can write it down, and that's easy. And probably if we are to prove that this is extremal, then as a corollary of the proof, we will get that bound.
Yes.
I believe and I hope. But as I said, this is just a hope.
Okay, so two questions. One is, so this is, we obtain this by joining all the roots of P.
Yeah, this is just
All the
QP abelian
Q's roots of P.
adjoint. Yes. Qth roots of.
Yes, okay.
Yeah.
And in extremal, the correct way of phrasing it is if I take polynomials over O,
Oh, the valuation ring,
or
yes.
the valuation ring, and then I say the maximum is attained.
Yes. Yes.
If it's non-trivial.
Yeah, and of course that is very difficult because it's talking about polynomials in two or more variables. I mean, we do mathematics in one variable, and the algebraic geometers do mathematics in two or more variables. So they live one floor above us, but we can still try.
Do you know by heart the proof for FP double brackets T? Why this is extremal? This is already a non-trivial fact, right?
It's not so hard. It just uses discreteness of the value group. That makes life much easier. In the divisible case, it's like here. It's much harder to prove extremality, but still, it should be doable.
Okay.
So the first thing would be try and prove that this is extremal and obtain the bound, and then we can formulate it in the first order way. But then there is another question related, and that is that we have another model of our theory, which is just the algebraic part. And of course we can do the same thing here. So here we have Q bar, and then that is below here. And then let me put that more nicely. And then we get fix intersect Q bar here. So we have exactly the same z hat dashed extension here. And the point is now, if this is first order expressible, the extremality of this guy, then it should also hold here, and then this should also be extreme. And here is my problem. Extremality is something which sort of calls for a kind of completion, because it says something can be realized.
But not a Henselian type completion.
But not a Henselian type completion. It's a more two-variable, say, kind of completion. And somehow I have the feeling that this is much more difficult to obtain in countable structures. Now, of course, the analog in positive characteristic, where we have FP double brackets T, which we know to be extremal, and because there we know about the field itself rather than about an infinite extension, this is first order. And then, of course, we have this field FP
T
double brackets T, exactly, intersect the algebraic closure of FPT.
Which is just a Henselization, right?
Which is just a Henselization of FPT with respect to the theoretical elevation. And if they are elementarily equivalent, this is also extremal.
But it is not known whether it is extremal.
It is not known whether it is extremal. It is not known whether they are elementarily equivalent. So if one could show that this field is not extremal, that would tell us that extremality is a feature which in a first order way separates FP double brackets T from this field. And we could possibly have the same situation here. Now, the argument that extremality calls for some kind of completeness and therefore countable structures are unlikely to have it is of course not a good argument, because we know by Leeuwenheim-Skolin there is an elementary substructure F which is countable. And because this is a first order property, it will also be extremal. So,
and Henselian as well.
Henselian anyway, yeah.
Henselian, yeah. But extremality doesn't. Does it imply Henselian? No.
Extremality implies Henselian.
Oh, it does. Okay.
Yeah. And yeah, everybody is Henselian anyway. But you're right. Okay, well, one has to say that. So of course, the argument that extremality doesn't happen in countable structures is plain wrong. But the intuition,
but in a different sense, it could be right.
In a different sense, it could be right. And so I think one project would be to try and prove that this is or is not extremal, and then do the same for this, and then hopefully prove that this is extremal, and then we can go down. So there are various avenues how extremality can, after all, be useful for us, with lots of question marks on the way.
Do you know what happens with extremality when I take the perfection, let's say, of FP double brackets T? Because Franzi and Costas...
Oh, the perfectal.
The perfectal. I mean, the Francis and Costas prove that this is then an elementary extension of that part.
So you're saying we go to FP T perf, and if we call this K, then you can go to K perf.
Mm-hmm. I believe they showed this as an elementary substructure.
I think that is correct. Yeah, that's
So
true.
by removing all the piece roots, the trouble disappears. But my question is, do you know what happens with extremality when we pass to this non-discrete valuation?
That it's not extremal.
It's not
Because the value group is just 1 over p to the infinity z, whereas extremality implies the value group is either a z group or divisible. So what one would have to do is to pass to FP double brackets T, join all nth roots of T, and then I have no idea.
I see.
I have no idea. One other thing which we may want to consider, and I'm not sure we have ever considered it. We looked at QP abelian and then the algebraic part. This is a huge jump, and conjecturally these are all elementary substructures. I believe what we haven't done yet is move up to QP abelian completion. Because this is not complete, because it's an infinite extension of QP. And then...
But that extension is just an elementary extension.
Do we know that this is an elementary extension?
Yes, I think so.
How?
Just by Francisco or Costas, or we can just say by Vandendriess's AKE principle. The point being that, I guess here, if we compare the reduced residue rings,
they're isomorphic.
they're isomorphic, and otherwise they're isomorphic, so the completion disappears in the reduced residue rings. So in fact, And in the value group, well, nothing changed there.
No, it's all immediate.
Mm-hmm.
Now, couldn't we say the same then here? Because I thought at this point we do not yet know whether that is an elementary extension. With exactly the same argument.
This is actually is it the completion?
No, it's not complete.
It's not complete, but it's on the way.
It's on the way, yes.
So it's on the way to being complete.
So if we go to these guys, QP intersect Q bar and here QP, then of course we know that this is a countable union of finite extensions of this, and all of those we know how they behave, and all of these are elementary substructures. So possibly it's again your inverse systems argument, which could show us, in fact it's a direct limit, so maybe one needs a direct limit version of that, that indeed this is an elementary extension of that. That is, I think, a nice further question here. Do we know either by this or by this sort of finite approximation from below method that they...
I see. Say that maybe it's much simpler than we thought?
Possibly.
I mean, the special feature about QP abelian is just the fact that this fifth axiom, which just says that the algebraic part is that, oh no, sorry, Q bar, that the algebraic
is the correct one.
Is the correct one. I mean, the fact that it's not trivial that this is actually a first order property. Or a recursive first order property.
One has to say something, yeah, but it's not hard.
It's not hard, but it uses the fact that one has just finitely many extensions away from QP.
Yeah.
To encode all the formulas. I mean, I wrote it down in the transfer.
Yeah, I know,
obviously. Yeah. So, but now I'm confused. Assume it's true that this is an elementary substructure of QP abelian. Wouldn't that give a very simple axiomatization then? Even too simple?
What would the axiomatization be?
Okay, just fix the axiom for the algebraic part.
Okay.
Mix tensilium.
Okay.
And
you have to say all the other 6 axioms as well, I believe.
But where did we use the, let's say, the 6th or 7th axiom?
We know they're both true.
No, we know they're both true. That's a good point.
I don't think it would simplify the axiomatization in any way whatsoever.
We don't. I think we don't get, even if we know that this is an elementary substructure, we don't get an axiomatization just out of that. No. No, you're right. Yeah. Do you have that transfer thesis here? Or
I do.
Could you? Yeah. Did you write on the last page that? Let's check. I see. So I only wrote down this so that the completion is an elementary extension of QPAB.
Oh, there it is.
But I didn't write this for the algebraic part for some reason. Yeah, probably because I didn't see that the algebraic part also has the same reduced strings. Or probably as the semi-reduced root.
I would think so.
Yeah.
I would think so. Yeah, I think that's worth double checking, but
Yeah.
it looks all right.
Yeah, I guess I have to learn about extremality now and read.
Yeah, well,
papers.
it's 10 years ago that I have read about
Yeah.
it. I've forgotten most of it. But
As far as I know, the people that used to work on it now are working on other projects, right?
I think it was considered like a dead end.
Yes.
But I think it's still the most canonical extra axiom on FP double brackets T to make the theory complete. Well, decidable.
It's the only candidate we have.
This,
Anyway.
Yeah, well, there were very complicated candidates Koenigsmann has come up with as predecessors, but they all follow from extremality. So this is the only candidate which is left over, which survives.
I see.
But people just didn't manage to prove anything further.
It's interesting that one of your, so the seventh axiom
Yeah.
you propose, it follows the Vandenbries philosophy in the sense that with the surjectivity of the Frobenius for k equals 1 is one of the axioms.
Yeah.
So the question is, how deep does one have to go? I mean, one of the interesting things is for any fixed formula phi, I only need finitely many elementary equivalences. Just a compact.
Yeah.
So, and it might be that one doesn't have to go really
Very far, yeah.
very far somehow.
Well, that was actually only a sidetrack.
Oh, that was just a sidetrack.
Yes, because I think you said you had another thing you had been working on.
No, I actually was working on the Basel.
Oh, okay. So, in that case, I think there are all those question marks. So, is this one true? And then we have is this one true? Okay, yeah, we've got that. And then if this is true, do we have the bound? That sort of follow up. And here we only know that it's it's existentially closed,
I think well known it's existentially closed.
but we don't know that it's an elementary substructure.
No.
No. So again, the same question here. So is this guy here extremal? This is one thing which is perhaps not too hard to check. And
If it's an open problem, probably it is hard to check.
maybe people just haven't tried.
Okay.
So here is another pair of question marks. Happy with that?
Yes.
Okay.
Oh, cool. Yeah.
Then are we moving on to something else, or shall we call it a day?
I think I have lots of things to work on now.
Okay.
Lots of open ends.
Brilliant. In that case, I guess we finish a bit early, but that gives you more time to work on the things.
That's right.
Very good.